So this is sort of a bit of a mishmash of a talk. I mean, everybody is familiar with computers, from cell phones to laptops to desktops and things like that. And you've heard about data centers and things like that. So that's what I sort of mean by at scale. And so I'll try to give some perspective on that. Sort of what are the challenges that come with thinking of computing at that scale. And so that is not a typo. So let's see that. Okay. So let's see. Okay. So I'll just basically be talking mostly about the past, about the now, and there'll be some technical stuff, but mostly. So feel free to interrupt and make it more interactive. There's not. Most of this is just personal perspective, and I've been careful to keep everything in the public domain. Sourced everything from the public domain. So, not where now. It seems, it's not on the slide. Okay. So, a little bit about design. So from my perspective, the designs result from understanding trade-offs. Trade-offs are driven by what your application is, what the underlying technologies are, what sort of cost performance trade-offs you're looking for, and in sort of what's pushing data centers are those three factors, among others, I suppose, but those are the primary ones. So the past, so you might have seen pictures like this. This is going back to probably the 40s and 50s. This way. The computing horsepower here is much less than what you have on your desktops or your phone. They were huge. I don't know if you can read that. So this is comparing sort of the ENIAC with the Intel Core Duo chip from 1948 and 2008. So the ENIAC could do 5,000 additions per second, and the Intel will do 21 billion per second, and so forth, and a whole bunch of things. And of course, the ENIAC weighed 28 tons, and the Intel chip doesn't weigh very much. Right? And the ENIAC consumed 170 kilowatts of power. The Intel was like about 30-40 watts. And so forth. And it cost a lot of money too. So the old machines were very power hungry. In fact, even as recently as Cray had more patents on cooling technology than on architecture. And this number is a little old. It's at least 4 or 5 years old. Whatever I could find, I don't know what the current number is. So even now, that's $8 billion in electricity bills for these data centers. Right? Any idea how many data centers are out there? Okay. So this is another picture, old, and now you have computing power in that which far exceeds whatever was there. Right. So there's also a bit of social perspective, like if you notice the pictures, there are women in there, all the pictures in the old computing. So well into the 60s, most of the programming was done by women. Till men realized that there's glory in programming, and women kind of got shunted out. So in fact, some of the early, so the social history there is that when they first started looking for people to program, they thought of this as an extension of the stenography pool or the stenographer's pool, or like the secretaries, because they construed it as being something like entry. And which was initially tended to be mostly women. The other source was also, before they had mechanical and electronic computers, the military employed human computers. These were actually people who had a good background in mathematics, and they were used to compute artillery tables and other things that they needed in the military, and often a lot of them used to be women again. So, sourced from those two sources, like in some other similar sources, there's another story. IBM was looking for programmers, big, they had a demand, and so one of the things again they did was they basically recruited from their employee base and basically asked for the spouses to come in and take tests, right? And so again, there are many such stories you'll see. And I've given a link here. I have the PDF of this article, Making Programming Masculine. I can forward it if anybody wants to read. So, and not only that, in fact, look up the life of Admiral Grace Murray Hopper. She was one of the pioneers. Many of these women found some of this work, doing this programming in binary, very tedious. So they actually, just to make their own work easier, they wrote some of the first assemblers themselves. So many of these tools, some of this stuff was actually developed by them. So this is sort of an interesting backstory. It is just sort of sad, but so well into the 60s, and then things changed. Okay, so coming back, so this is what your typical sort of computer abstraction looks like. You have a bunch of processors, or the CPUs. There is the L1 caches for each processor. So it's just like very high-speed local memory, right, which is there. And then there is a shared, so that is, each processor has its own level 1 cache. And then a bunch of processors will share a level 2 cache, let's say, which is slightly slower, right, or maybe the same speed. And then you have shared memory, which are those memory cards you see, the DIMMs. Right? And then you have this. And so here you have some relative performance numbers here for what a DRAM is, like what its capacity is, what its access time is, and what its throughput is in terms of data it can transfer. And you can see, there's a whole hierarchy. These two work pretty close to the processor speed. This thing is slower, and then this is dramatically slower. Though, as you go from here, the performance gets lower, but capacity goes up. So it's a trade-off between capacity and. So now I want to show you some other pictures. So this is a different kind of computer, literally. This is what the data center looks like in some sense. So there are some very nice pictures, and I have a link at the end. You can go. Google commissioned a photographer to visit Google's data centers, and there's some beautiful pictures. They're available on the web. So these are all pictures from her collection. These are and then there's a lot of infrastructure required to support that kind of computing. So this is literally, I believe this is basically cooling. You can see the plumes. Just to give you an idea of the scale. So actually, in one of the data centers, I believe in Finland somewhere, they power a sauna room from the heat generated by the.
There's one in Greenland somewhere. They're taking the water from the ocean and then they're cooling it off.
That's one of the places. Yeah.
And before they let it back in the ocean, they again mix it with some cold water so that they're not disrupting the temperature of the.
Yes. These are some more pictures.
the significance of the colors in the plane?
You can tell. So yeah, so you've seen the Google logo has some colors, so you will see that theme showing up in various places. These pictures. These are bikes on campus to go from building to building. So somebody put one of those bikes there for a picture. Right, so now you're actually looking at some of the servers in here. Cabling. So yeah. So network as a computer, you have a client server. With a data center, resources become fungible, right? They're interchangeable. You don't even know what's happening. You write a program and you say go, it gets. So you have all these servers in the data center. There are layers of software on it. You send. Not only do you issue your, you have your program, but along with that you request what sort of resources you want, and then off it goes. It gets deployed and executed on some set of machines. You have no idea where exactly. I guess if you want to, you can find out, but you typically don't need to. So that's sort of most of data center. So that's again some more pictures of what that looks like. Now, so the next, so you saw the pictures of the racks. These are the racks that you have here. So now you have one of those servers, but now on a rack, effectively, you have a whole bunch of them connected to a rack switch. Like the network. So now if you look at the whole rack as a machine, now suddenly you were talking about each server is 16 gigabyte, but now as a rack it has got 1 terabyte. Disk it has 160 terabyte, and now everything is scaling here. The disk doesn't necessarily scale, the seat time doesn't scale, but capacity definitely scales. So you can see sort of certain things scale and others don't. So that's going to determine how you do your compute or how you balance your resources. So I'm going to intersperse pictures, pretty pictures in between. To just give you a sort of idea of the scale of these things. And so now you go from a rack to an entire cluster, which is some number of racks working together. So part of this structure is different. It is defined as how they are hooked up together. And it's not just like the computer. You have to also think in terms of how you supply power to this. So the partitioning of the power domains also is something that has to go in with this. So that a power failure, how it affects this structure, is a non-trivial problem.
Moore's law is still holding up.
No.
Whose law?
Moore's law. So Moore's law is beginning to flatten out. That has a lot of implications.
Are we any closer to moving beyond silicon? I mean, CNT or something like that?
Nothing really at this stage. I mean, a lot of, I think, but nothing practical.
What about a quantum computer? They last week?
Yeah, what about the D-Wave thing? That's...
It's an experiment. It's a research problem. Experiment.
These kind of data centers are in each geography?
There are many of them in different places, yeah. So that's another thing is that we'll get to it in a minute. So how many people watch Star Trek? You heard the phrase Jeffrey's tube. This is what it reminds me of. Jeffrey's tube. I don't know if you anyway, we keep opening and going into it. But this is sort of the back side of the server solver. I think all these are fans, so all the air comes up with this. So, going from a data center now, you can sort of think even bigger scale, they call that warehouse scale computing, and finally sort of planetary scale computing. You're providing a service like search all over the world, and you can see in any geography, the search load has a certain distribution. Starting in the morning, in the middle of the day, end of the day, overnight, it's like pretty low. But then somewhere else, there is lower. So, either you have to geographically distribute your compute resources or have to move your search requests around to different parts of the world. So that's why you have to think. Once you're providing something globally, you have to think at that level also. Now what happens here is that what matters here is the aggregate performance of the entire system. Not just one machine or some sort of, but everything. So that's sort of an idea of some of the distribution of some of the centers around the world and how they're connected to data centers. Okay, so going back to the question of how many data centers. So I just did some search. I did the search a few years ago. I haven't updated it, but even then, will give you an idea. So, for instance, there are 1,000 co-location data centers. I think that's now pretty well known. And according to this source, it came up with something like 13,000 data centers, of which more than half are in the US. I think again that's probably changed a lot by now. A large number owned by
Not Google.
right. So this is another interesting chart which sort of shows you as you move and start looking at these different resources at different levels of abstraction as you move, how their aggregate performance changes. Some things go up and some things actually get, bandwidth is actually getting scarce.
What are the two axes?
This is just magnitude. This is local DRAM, local disk, and so you're looking at bandwidth, latency, and capacity. So capacity goes up easily. But now you also have latency, which is kind of, you try to keep latency accurate. Bandwidth, obviously, because you're going to have bottlenecks when depending on the topology you have, it's going to be. So, you look at the relative position of these things for a local CPU. And here, it's a different distribution. So that's going to cause you to think differently about how you do things. So assume you have super reliable servers, right? Mean time between failures is 30 years. Build a computing system with 10,000 of them, and you want to watch one fail every day. So, fault-tolerant software is inevitable. Typical yearly flakiness is like 1 to 5% of this will crash. Servers will crash at least twice. So, And again, some of these numbers and some of these ideas are like a little old, so things have become bigger since then. So it's like, you might, you might have a warehouse scale computer if you get paged in the middle of the night because you only have some few petabytes of storage left. So again, this is sort of a repetition of some of the other stuff. So this is an example of, so again, this is an older system where the file system stored data. There's a lot of replication and encoding that goes on to overcome the flakiness of the hardware. So there's a lot of duplication. And there's also so one is to for redundancy, but the other is you can also take advantage of this for improving your performance. But if you spread your data across in such a way that you can access, the bandwidth from here is limited, so you can access all of the files from C1. And if it continues into C2, then you can fetch from here instead of fetching from here.
Geocaching.
Sorry?
Geocaching.
Not necessarily geo, it could be in the same data center. But the idea is that you have that trade-off. Yeah, and you can to protect against say like some natural disasters like fires or earthquakes or something which can affect the whole data center, you might want to do this kind of duplication or replication across geographies.
Generally, how many copies of
That varies depending on what you make your data.
what is available?
So again, this will be the sense of all that. So again, this is it's kind of nice to have this. Come on in. Hey, come on. Kalish. So this is just to motivate. So we'll go forward. But if you think of, we talked about a server, L1 cache reference. So that's about half a nanosecond. So these are sort of if you have some handy numbers, they're like building blocks to do analysis basically. So you have branch mispredict. That's your cost. Now L2, that's the shared cache. Reference is 7 nanoseconds. If you want to have mutually exclusive access to some part of the memory or some data, then getting the lock to it, unlock, doing it, so there's a cost associated with that. Main memory access. Compress 1 kilobyte of data with that protocol, it takes that much. Sending this much data, reading this, and so on. Now you see it goes from half a nanosecond all the way to 150 milliseconds for sending a packet from California to Europe and back. Right? Disk seek is like one of those problems it's a physical problem. So disks are increasing in capacity, so they can, the footprint for storing a bit of information is shrinking. But the speeds at which the disks rotate don't change that much. So the time it takes the head to seek, the number of I/O operations you can do on a disk doesn't change much while the capacity increases. So now your ability to go and read and write is more or less unchanged, but you can pack more data in there, and that has issues.
But is this true for magnetic drives or versus the SSDs also? So does it change?
So SSDs also they give you a jump in performance, right? But also at a cost. And their capacity is, for the same cost, is much less capacity. So now, with that information, you can quickly do some back of the envelope calculation, right? So if you have a single server, so how long to generate image results page? If you're doing a search and you want to get the image, thumbnails of the images, so you want to get 30 thumbnails. So you do 30 seeks, assuming they're all at different places, right? At 10 milliseconds per seek, and then you do plus 30 times 256K, that's the size of the image, and that's the bandwidth that you have. So that's 560 milliseconds to, no, a quick back of the envelope calculation. So it'll half a second. So you have that, but you can also do the following, where you can do this across different disks. So now you parallelize that, and you can drop the cost down to this. So in reality, even now you are, when you're doing it on one machine, it's fine. But now when you go to so many different machines, this is sort of a simplistic answer in the sense that it ignores variance. So what is this? What are these variations? Right? Now you have different machines, there are different things going on them. So now the caches are in different states, pre-computing. So this calculation that we do here ignores a lot of these sort of unknowns, which they're not easy to predict. You don't know what's going to happen. So then this is sort of the empirical solution. You go write little and benchmarks, you do it, you profile it, and you get some information. But now this is going into some other things that you have in your software stack. These are various resources. So fundamentally, you need to have that kind of understanding for these various pieces in your system to get some decent back of the envelope calculation. So now we get to the tail. So this is sort of what I was leading to, right? Is so in general, design for low average times. So in general, you would think that when you're doing this aggregated thing, you're trying to make your average times to be low. But actually you have to worry about your 99th or 99.9 or 99.99 percentile. Because typically you will have some sort of distribution like that, and then there is this thing that just goes on and on and on. And so this might be your 99, and somewhere 99.9 and so on. So if you have 100 servers, you're going to hit that case, and so on. And so if you're looking at the aggregate performance, it's you've got a job and you've given bits of it all over the place. To get your answer back, you have to wait for the last guy. And if the last guy is somewhere in the tail, then your performance is going to be limited by that guy.
You don't have to wait in this kind of.
Huh?
You don't have to wait for the last day.
So that's one of the. You have to build it into that. Right. So where does all this variability come from that leads to this tail behavior? Right? Shared resources. Machines might be shared by different applications contending for shared resources. And there are different things running on different machines. So they're all in different states. Background daemons may only be, may use only limited resources. So there are global resources. This is like at the network level. This is at the machine level. Then there might be other things going on these machines. Like some machines might be doing some background jobs, might be running some debugging, doing some other work. And then because of going across the network across different layers in the stack, there's queuing and more. And again, you don't know what the state of the queues are in different places. Some might be longer wait times, there are more stuff in it. There are also variability due to several hardware trends, right? So there are power limits. So if something starts running high, it gets, high, its power consumption starts going up. It's getting hotter, so it might get throttled. Garbage collection. So this is with respect to solid state memories, defined devices. And then again, energy related. So again, a quick. So assume a system built with servers, right? So the typical response time is 10 milliseconds, but the 99th percentile response time is 1 second. Okay. Now, if the user request requires a response to be collected from 100 machines, then statistically 60% of the requests will see slow times. With a single server slow time response of 1 in 10,000, a 2,000 server group will see we slow almost 20%. So these are some of the charts that you will get. So this is sort of some real actual.
In which paper is that from?
Huh?
Where is the data from?
This is from some papers that I've referenced to. And then I've taken some slides from Jeff Dean's talk. Public domain. So these are more, I won't get into too much. But okay. So there are certain things you can do to get around these kind of problems. So now there's a trade-off. If you want your answers in time, then you can use more resources. And as soon as you have your responses, send requests to more than one for each thing. And as soon as you get all the responses you want, then you send a kill signal to the others. But there will be some cost to that. So now this this doing things in this fashion leads to a whole bunch of other solutions that you have to resort to, and there's some costs associated with it. So now at the data center level, as you're doing work, you also start monitoring how these servers are performing. Right? And if you see somebody repeatedly behaving badly, then you start isolating them. So now you start building layers of software in your system to do all these things. So over time you build a lot of intelligence in these systems. So this is what Mosh was saying. You don't have to wait for everything. Sometimes good enough is fine. There are many applications where, if you're doing search, you don't have to wait for every last bit to come in. You can start giving the user some information right away. Then the canaries. You send before you actually send the full-fledged request to everybody, you send little probe requests to see how things are going, and then based on that you decide how to. Storage. So storage is a big part of the data center. So the problem here is that capacity is increasing, the ability to read and write to the disk is more or less flat at what speed it can. So now you have more and more data hidden behind the same pipe, and that creates a problem. So you have to rely on having new technologies. So you might add more hierarchies of storage, and now you have to find ways to think of classifying your data in terms of certain data you would classify as hot data that you might want to spread out for quick access. And then there's some data like in your email, which any email is more than a month old, you're not probably going to look at it most of the time. So that could go to some stored differently from things like that. So I just put this because tomorrow the movie's coming out.
Which movie?
There's a stormtrooper in the data center.
Oh, okay.
Yeah. So these are I think I'm pretty much done. I can share the sources, and if some people here might know, if people are interested in computing history or some of these kind of things, these are some of the things that I share with my interns. There's an article that was published in 1945 by Raminder. Anybody familiar with it? Has been a thing? Okay, cool. That's a great article. Anybody else? No? If you haven't read it, highly recommend it. It's available on the web. Just search for As We May Think. Raminder was like the engineer to the country, and he was one of the people involved with organizing the effort for the Manhattan Project also. So in 1945, in that article he writes, there's a quote from there, "The age of cheap computing devices is upon us." And like what it will mean. And his insight is amazing. And not everything that he talks about has happened yet. And many of those things have actually come to pass. And then there is another report from 1962 by Doug Engelbart. Anybody know that? Okay. You know who Engelbart is? He was, among other things, he was instrumental in designing going from a line editor to a page editor. And then the problem was that on a line editor you would use a cursor to move back and forth. But when you go to a page editor, a cursor becomes painful. So he designed the first mouse as a pointing device to move around. So as a fresh grad out of grad school, he wrote a proposal and got a grant from the government, Air Force, and he wrote this report. It's called Augmenting Human Intellect. And in that he talks about, it's actually a nice thick report, but it's very, very, very worth reading it. And again, in that he talks about, we should use these machines to, and he also gives credit to Vannevar Bush's article. He says we should use these machines to augment humans. And so then he talks about, think of an office where you work is your workstation. So a lot of this terminology comes from that report. And you have a filing cabinet with folders in them, and there are files. And all the terminology is now, and it's all from the history. It's a really interesting report. And again, there are a lot of things in that report that still haven't happened. So if you're looking for ideas.
That was a Xerox part.
Huh?
That was a Xerox part or what?
He was at SRI, Stanford Research Institute. And a lot of people, when his grants ran out, a lot of people left his lab and went to Xerox. A bunch of those people then took it to the next level. But he died like just a few years ago.
Yeah, 2-3 months ago.
Huh?
2-3 months ago, maybe 2-3 months ago he died.
No, a little longer than that. Yeah, pretty recently.
Very recent.
I don't know if it's just months, maybe. And on YouTube, you can go and look for what is called the mother of all demos. If you can find it, you'll see him giving this demo in 1960 something, in which he set up a link between Menlo Park and SRI and San Francisco, and he did a video conference live. And in that, he's got hypertext and he's accessing data in different ways. He's doing all kinds of stuff in those days. All right, any questions?
Google Compute Engine, that web service, computing service, it runs in the same infra?
Yeah, I mean, fundamentally, the database is running in the data center. But I think you have to think of that.
Millions of times. That millions of times less work than this laptop. So do we foresee that the data centers will also eventually become obsolete with new technology?
It's hard. I mean, so yeah, the story might be a little more mixed. I mean, they will continue. It's not that desktop computers go away, something else comes in addition. So there will be other layers that might come. There may be other things that come into augment. The data centers themselves might evolve. I think you're already seeing some of that in the sense that originally data centers, it made a lot of sense to make data centers as homogeneous as possible. So every all the resources are just interchangeable. So your scheduling, your management, everything becomes easy because all the building blocks are the same. But now, as application diversity increases, your computing platform, your general purpose computer is not the best solution for some applications. And if some of those applications which are not very well suited on CPU, but its compute footprint grows in the data center, then you might consider going to a more heterogeneous system where now the heterogeneity might come, you might have the same building block in terms of CPUs, but how you structure them, how you connect them, how you do things, there might be heterogeneity there. But you could even go to the level, let's say, like the CPUs themselves, but not something that you want. You want some other kind of compute device there. So even at that level, think of having heterogeneity, which makes your management and your sort of configuration and scheduling more complicated. Sorry, yeah.
So can you give us a sense of this application diversity? You were talking about the 99 percentile and the 99.9 percentile. So these are applications which the data center designers don't quite understand yet because they are new applications which have requirements that are different. I mean, so much of efficiencies come from knowing, like you gave the example that a month-old email you're unlikely to access it very quickly. So, the tight binding between applications and the architecture on which it runs starts to change when applications become diverse. So give us a sense of what kinds of applications.
So let me just first go back and clarify one thing. So when I say 99 or 99.9 percentile, it's for any given application. So you have a given application, and what you do is you break it up into many parallel chunks, and you issue it to run on so many machines. So I'm talking about the percentile behavior for that, for any application. For instance, one of the things that everybody, not just Google, is looking at is that the keyboard is this historical artifact that we inherit from the typewriter to this thing is there. And it served us very well. But now when you sort of go to these kind of devices, the keyboard is not a very nice thing. So here now you have things like I can say, okay Google, and I can ask it questions. It's listening to me and it's doing, it's giving me some responses. So that's a much more natural interface. Speech recognition is not an easy problem. It's pretty hard. Even if every user, so there are like 1 billion Android phones out there. Every Android user spends just 2 or 3 minutes a day talking to their phone. That's a tremendous amount of compute load for the data center. Now you might imagine going to the next level where say you have visual interfaces. So like Google Glass or some equivalent of that. You're looking, it's there, and then you say, oh, so what am I looking at?